Okay, now we're on record. Okay, someone's saying in chat that okay, very good, good travels. And if you are watching us, whether online or offline later, you can also have a little cup of tea and drink it as you participate in this lecture, whether in person or offline. This is lecture 4, sorry, in high-dimensional probability and applications to data science. Last class, we went pretty far on this in this story, in this road, which starts with probability theory. We proved approximate Carl-Pajor theorem using probability. Approximate Carl-Pajor basically tells us how to shorten convex combinations. If you have a very long representation, convex representation of a vector, you can shorten it. You can make it approximate, but it will be much shorter. Using that, last class we proved we analyzed covering numbers. Now, the covering number is basically how many balls of a given radius. It's an ellipse here. How many balls of a given radius are needed to cover a given set. So in this case, I'm trying to draw the balls of the same radius here, radius epsilon, let's say. And here we go. So this is my set T, and this is maybe a ball of radius epsilon here. And the covering number of a set T, it's very geometric, very simple notion, is the minimal number of round or Euclidean balls of radius T. Of radius epsilon, excuse me, radius epsilon, that suffice to cover, that need to cover T. So in this case, yeah, and it is denoted n T epsilon. In this case, n T epsilon is definitely, well, we were able to cover it 1, 2, 3, 4, 5, 6, 7, 8 by 8 balls. And I put this inequality because maybe there is a better covering. Maybe there is a covering with 7. But okay, remember, so this was a definition that we gave. We can think of a covering number as an important measure of size or measure of complexity of a set T. It has advantages and disadvantages over classical notions of size. For example, volume. For example, flat sets T. If T is completely flat, then the volume is 0, but the covering number is not 0. It still captures the size, the complexity of T in some sense. We then showed 2 surprising things about covering numbers. Well, first of all, let me actually tell you this. Covering numbers is actually, I do not know if the covering number can be computed exactly in polynomial time. So computationally, it's not clear to me. I think it's kind of maybe it's an NP-hard problem. I'm not so sure, generally. I don't know, no. Well, even in dimension 2 or 3, it could be very hard. Even for a circle, it could be a hard problem. Take a circle for T, and how many little circles you need to cover, the minimum number. It's not very clear. So exactly, exact computation could be very hard, but we're interested in at least an approximate computation. And there are surprises now. In high dimensions, there are surprises about the covering numbers, and 2 of them is this. So first, that we showed, is that usually the covering numbers are exponentially large, exponential in dimension. n. So t is in Rn. Exponential dimension n. For example, the covering number of the unit ball itself, if you want to cover the unit ball by copies twice smaller. So we're trying to cover the Euclidean ball by the balls that are just twice smaller in radius. That requires at least 2 to the n balls. It's crazy, right? In the plane, nothing like that happens. You can cover a circle by radius, by smaller circles. You don't need exponentially many, but in high dimensions you do. And that is a general phenomenon. If, for example, you want to cover the cube by balls like this, small, same thing. It will be exponential. However, that's what we showed, is for polytopes with few vertices, for багатогранники, for polytopes with few vertices, with polynomially many vertices, covering numbers are polynomial, are not large. That's also surprising. So if P is a polytope with m vertices, and for scaling we assume that the diameter of P is less than 1, then we can cover it with something that's polynomial in m, in the number of vertices. Okay, so for example, for the simplex is a generalization of a triangle in high dimensions. In 2 dimensions, it's a triangle. In 4 dimensions, it's called a tetrahedron. Okay, so in n dimensions, it's just n+1 points, and you take a convex hull of that. For that, you have m equals n+1. And so the covering number will be exponential in n, or polynomial in n, actually. Okay, that's where we stopped. Okay, so far so good. That was last class. Cool. Good. Okay. So now one of the most surprising. Now we're coming to one of the most surprising phenomena in high dimensions, where we make just one last step on this road that started from approximate Carl-Pajor. Look at this theorem and say, hey, here's the covering number in the last result. Covering number is small, it's polynomial. If the covering number is small, then we're able to cover P with small number of small balls. Small number of the balls of radius epsilon. Then these balls collectively can't have big volume. It's small volume, right? They cover the small volume. And therefore, the volume of the polytope itself must be small. The volume of the polytope will just derive it from this almost immediately, that the volume of the polytope itself in high dimensions is extremely exponentially small. Crazy. Okay, let's try to state and prove this. This is an important result, and I'm glad that in let's call it volume of polytopes. I'm glad that in about 3 hours or 4 hours of lectures, we were able to come to the result that's recent. In fact, it's well, approximately recent. It's a result by Carl and Pajor, both of whom are mathematicians that are alive and working in. Pajor works in Paris. It's a result from 1988, where he was a student, graduate student. Pajor was a graduate student. And here's the result. So suppose we have a picture like this. Let's say we have a polytope in a ball like this. Anything like this. This is P, this is B. So let B be the unit Euclidean ball, and P be any polytope with m vertices, then the volume of P is super, super small, extremely small. And we will prove in a second that this will prove this estimate. 4 roots of log m n to the power n. So it's a deep result. And what I want you to do when you look at these results, and they may seem overwhelming, all these 4s and roots and logs and exponentials, is to see what actually is, what is it saying? What is it telling us, the right-hand side? Disregard 4 for a moment. Think of that 4 is non-negative. 4 is not, it's just a number. I couldn't get the better number. Maybe there is 2, I don't know. Doesn't matter. Disregard the root for a moment. What's most important is that there is an exponent in n that drives the whole expression, right? There's an exponent in n, and is this number big or large? Well, that's going to be, probably is going to be small, right? Because logarithm is usually smaller than, logarithm grows smaller than linear. So this expression, this whole expression will be exponentially small, something like, I don't know, less than e to the minus n, for example, unless the number of vertices m is exponentially large. I'll put some unspecified constant c here. Right, so in the right-hand side, the log is trying to fight with n. They're kind of in juxtaposition here, right? And unless you take m exponentially large, so that it kills the log, this number, this ratio will be smaller than 1, and so exponential will be very, very small. So this volume here, is super, super small. It doesn't make sense in 2 dimensions, right? In 2 dimensions, you see how can it's small. Oh, it's about 1/2 of the circle, but in high dimensions, it's very small. Okay. Here's what happens now. I'll ask you about whether you understand the statement, then we'll prove it, and then we'll try to make sense of this, try to correct our intuition. Okay, is the statement clear? Yeah, good. Okay, good. Okay, the proof should also kind of be clear. I already explained it. Let me explain again the idea of the proof. The result that we proved last time is that this polytope has a small covering number. So it can be covered by a small number of small balls. And then we just take their total volume, and it's going to be small. So since this covers P, the volume of P must be small. So that's it. Okay, so let's do this. Proof. By the definition of covering numbers, P, the polytope, we know that P can be covered by this many, by definition, this many copies of a ball of radius epsilon. Let's denote it epsilon b. Okay, nothing happened here. It's just a definition of the covering number. Right? The covering number tells us that this is how much you need to cover. Okay. Therefore, if you compare the volumes, we see that, well, the volume of polytope is smaller than the volume of by what it is covered. And by what it is covered, there's this many balls, each of which has this volume. Yeah, clear? This should be clear, right? You just cover it by this many copies of this ball. Therefore, this volume has it. Okay, perfect. Okay, and we know both of them. We know both of these things on the right-hand side. First of all, this one the covering number. This is smaller than m to the power 1 over 2 epsilon squared. This is from this result. Let me make it a little smaller here. Yeah, okay, doesn't fit in one page. Okay, so listen, we want to substitute this. There's just a little bit of an error I am making here. The diameter should be smaller than 1, and the diameter of the unit ball is not 1. It's actually what? Its radius is 1. Diameter is 2. Okay, but it doesn't really matter. That just affects the scaling. So let me skip this little thing. It will not be 1 over 2 epsilon squared. It will actually be 2 over epsilon squared. And that is just, I'm adjusting the scaling of these results. Okay, a little technical. Anyway, so this is from the last result. And what about the volume? The volume we know. The volume is, how did it scale? How can I take epsilon out? It's something times the volume of B. What is that something?
Epsilon to the
Maybe
nth.
to the nth power.
Yes, thinking it. It's epsilon to the n. That's how the volume scales in dimension n, right? The area scales like epsilon squared, the volume epsilon cubed in 3-dimensional, generally epsilon n. Okay. So when you compare now, let's just divide by the volume of B, move it to the other side. And the ratio of volumes is then m to the 2 over epsilon squared times epsilon to the n. Okay, so this is the volume ratio. What shall we do now? What do you think?
Minimized by epsilon.
Yeah, exactly. Totally. So the right-hand side has epsilon. And we don't want epsilon in our bound, but then we can think, what is actually epsilon? How did we even take epsilon? Well, we'll never even fixed it. Right? This argument, all of what we said is true for any epsilon. So this is totally true for any epsilon. So we can choose the best. The one that makes the right-hand side the smallest, which is the best for us. So we then minimize the right-hand side of this one in epsilon. And I'll skip this part. Yeah, you guys know how to do this, right? You take the derivative, and it's an easy derivative. You get the equation, it's an easy equation. I did it. That was my homework, so I did this. And the minimizer would be exactly this. So this is do it yourself. Just minimize that expression. Done. Any questions? Good. Okay, we proved that the volume ratio is this. Perfect. Let me copy this, and then we'll try to make sense, because so far it doesn't make any sense to me. And this is a picture. In low dimension, it doesn't make absolutely any sense that a polytope with reasonable number of vertices has exponentially small volume compared to the always exponentially small volume. Doesn't make any sense. So a couple of remarks. First a little remark is that this is almost the best possible. In fact, Carl and Pajor, the people who first proved this result, they proved a slightly stronger result with log of m over n instead of log m. This is very tiny improvement, but I'm bringing it up because that expression is optimal. So this is optimal. So what we proved is an almost optimal result, and it's attained, the lower bound is also true, it's attained for an interesting object. It's called a random polytope. A random polytope. It's a very active area of study in probability, in geometric probability, random polytopes. And you do it as follows. You construct the random polytope as follows. You take the unit ball. You take the unit ball B, and you just drop random points. Just throw darts on it. You can throw darts inside the ball, or you can throw the darts on the perimeter. Let's say you do this on the sphere randomly, independently, uniformly, like this, and then you take their convex hull. And the convex hull is called the random polytope. Here we go. That thing is P. So P is the convex hull of random points, m of them, where xi's are independent and identically distributed random vectors, random points on the unit sphere. So I'll denote it by like this, dB, the diameter of B. It's a very cool object. Throw points, take the random hull, convex hull. It's called random polytope, and it attains this bound. The lower side, the lower bound is also.
May I ask?
Yeah, go ahead.
What should be additionally be done in the proof to derive this like optimal estimation? Is it some complicated thing, or it can be derived relatively simple?
Yeah. Okay, give me a great question. I tried. I like spent maybe 20-25 minutes yesterday trying to see if we can improve our argument to get this optimal, and I don't know how. So if there is a way to do this, that would be great. Think about it if you know how to do this. What Carl and Pajor did was a complicated way. It was totally different, absolutely a different result. It was based on functional. I linked a paper actually to the lecture notes, and it's a complicated argument using functional analysis and deep resulting. It's kind of a soft.
Good. Mm-hmm.
Yeah. So yeah, I'll be very interested to see if there is a simple way, like based on approximate correct theory, to attain the optimal one. Okay, the fact that it is attained actually for the random polytope is even newer, and this is Daphnis. It's due to Daphnis and 3 other people at L3 in 2003 and 2009. I also linked the paper to that, I think. Okay, so this, we kind of cleared the ground here. Now let's look at this bound and try to make sense of it. Let's try to see what it actually is telling us. Okay, so the right hand side has this strange number. Let's say it's the number is 4 root log m over n. And so for this number, theorem says that the volume of P, volume of the polytope, is bounded by delta times n times the volume of B. Just rearranging the terms here. And we can now It's just a mental experiment. Bring delta inside. So it's a volume of delta B. So in other words, what we get is that the volume of the polytope here is smaller than the volume of a very tiny ball, like this, delta B inside. Well, this picture is totally contradicting it, right? The volume of, we're saying that the volume of the polytope, of this polytope, is approximately the same as the volume of an extremely tiny ball, delta B. And you look at this picture, it can't be true. And this was a very big surprise in the 80s, I guess, in the beginning of the 80s, where people started to look at this and say that doesn't make any sense. Geometry in high dimensions, not only, when you were like little kids, you thought, okay, there's 2 dimensions, there's 3 dimensions, and maybe there is 4th dimension, and the world in 4 dimensions looks so cool, and there is this cube in 4. Okay, so it's a fun thing in 4 dimensions, and I was fascinated by that too when I was a kid, and I thought, okay, maybe when I grow up, I'll start studying this world of 4 and 5 dimensions, and I did. But there was much more surprising that the world in high dimensions is not only an extension of the geometry in world of 2 and 3 dimensions, but genuinely new phenomena appear, phenomena that our brain cannot comprehend, our vision cannot comprehend, perhaps, because that really violates any intuition. And so to try to make any sense of this, Vitaly Milman, let's say it's for Vitaly Milman in the 80s, proposed the following correction. It's called the hyperbolic correction. To our low dimension and to our intuition. It's not a rigorous thing, unfortunately. We don't know how to place this rigorously, but this is how we now think of polytopes. Okay, so we don't think of them this way anymore. We change the picture mentally. It's a mental experiment. We change the picture to the following. Okay, the ball is still the ball. The points are still the points. Okay, so the vertices of the polytope stay where they are, but the polytope itself, look in your brain, should look something like this, like a hyperbolic thing, like a little tentacles coming out of. Okay,
you missed 1 point.
I missed 1 point. Yeah. Okay, 1 point. Come back. This may be. Yeah, like this. Something like that. Yeah. So the idea is, yeah.
But we've taken the convex hull of these points, and this thing is not so convex.
Exactly, Maria. This is where the problem lies. So now, we can't imagine things in n dimensions, what they look like. So we have to give up something, right? So the question is, what do we compromise? Where do we make compromises? And the proposal was, okay, let's compromise thinking about convexity. Okay, we can work with convexity analytically, but let's stop visualizing convexity, so to speak, right? Let's make this abstraction of convexity stay back on our mind, but not in our vision. So our vision should give up on convexity, and then the world is back to normal. Then the picture looks like this. This is our polytope P. Here, P. This is a ball B. And the small ball inside, to which it is comparable in volume, is like this, is delta B. And then we can think, all right, so delta B is kind of the core, or a bulk maybe, of this polytope. And the polytope consists of its bulk or core and little tentacles, very thin tentacles that don't contribute much to the volume. and the tentacles grow out toward the vertices. And there's a core, and these are tentacles, kind of. So this is so we give up visualizing convexity, but this way we visualize volume distribution better, volumes better. Okay, so that's what happens. Any questions? Okay, so hyperbolic correction may look like crazy because, right, there's no volume, there's no convexity anymore. And it's totally like a mental experiment that's unjustified, but it's actually justified. Here's an experiment that, in fact, you can check on the computer that it's that this picture is justified. Let's call it a blind spider experiment. So suppose that you have a spider sitting in here in the middle of this ball. So spider, and the spider crawls erratically, randomly. So the spider walks, the spider makes a random walk starting from the center, from the origin. So imagine you are like a spider and you walk and walk and walk in the polytope, in the polytope, in P. Imagine the polytope itself has the walls. The boundary of the polytope is walls, and the spider can just travel inside the polytope. What will the spider see, right? Where will the spider end up eventually? If you know a little bit about random processes or Markov chain, Monte Carlo, or something like this, then your intuition to say something like this, well, the spider could end up anywhere in the polytope. The volume distribution is a stationary distribution for the spider. So the volume is uniform, and therefore the probability at the end of time, after a very, very long time, the probability to see spider anywhere at any point of this polytope is about the same because it travels erratically. Okay, it's a good low-dimensional intuition. It's a terrible high-dimensional intuition. It will not happen, actually. What will happen is, well, most of the volume is where? Most of the volume is here in the core. And the tentacles have very little volume. So there is very little probability, exponentially small probability that the spider will even find its way to the tentacles. And therefore, the spider will stay almost forever, like for exponentially long time, will stay in the core, in the round core, delta, in this very tiny portion of the polytope, very tiny ball, will not, and the spider will not even find any tentacles, which are vertices. Okay, so if you look at this picture, it's kind of clear, right? The tentacles are very, very small volume, and so therefore exponentially small volume. Therefore, it takes spiders so long to find. Fine, but if you go back to the original picture, it won't make any sense. Right? You start the spider here, and of course, it will find its way anywhere. So the low-dimensional intuition doesn't work. The high-dimensional intuition actually works. In fact, the spider will not. Let me tell you one more thing. The spider will not even be able to tell the polytope from the round ball, from delta B. Imagine you are the spider and you're blindfolded and you can just sense the walls of this polytope. whenever you just hit the wall, you kind of come back, or maybe you do something else. So if you're in this position, then you will not be able to distinguish. You will not be able to tell where you are. You will think that you are in a small sphere, in a small round cell, delta B. So algorithmically, it's kind of impossible to tell the polytope from a sphere. If you just do this random walk. Okay, it's amazing, but it's actually bad for experiments. It's bad for algorithms, for Monte Carlo Markov chains. It's bad because the random walks, they can't even explore polytopes. All they can do is they can explore a very, very tiny portion of it. So for search algorithms, for example, this is bad. You have to imagine something. Okay, done. Any questions? Yeah. Okay, good. Okay, I hope this was intellectually stimulating. And we have finished the first story that started with probability, going through approximate Carl-Pajor, then covering numbers and volumes, and then hyperbolic intuition, high dimensions. This was our first tentacle, so to speak. So we go back now, and we will now begin to study probability in high dimensions and data science applications more seriously and in more detail. For that, we need tools. And what we'll first do is, and it will not be clear why it relates to high dimensions at all initially, but we will need to sharpen our tools. What we have now from the course in probability, that's not enough. We need new quantitative tools. The most important tool set in high dimensional probability called concentration. Concentration inequalities. And that we'll do first. Concentration inequalities basically say that a random variable, many random variables, okay, not all of them, many random variables stay close, very, very close to their expectation with high probability. And this high probability is higher than you think. It's like exponentially close to 1. So many random variables are very, 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 very tightly distributed around their means. And we will study instances of that and prove rigorous theorems about this. But today we'll just start from the simplest distribution, normal distribution. We'll just study the normal distribution a little bit. And you guys, do you know what this is? The notation for this, mu sigma squared? Yeah. A normal distribution, measure mean mu, variance sigma squared. You studied in probability. Okay. Good. Okay. So what do all the engineers know, for example? They know that the normal distribution, the 3 means rule, the normal distribution stays within 3 standard deviations from its mean with probability, with very high probability, with probability something like 0.9973. So yeah, it's a little surprising, I guess. This is just 3 sigma here, and this is 3 sigma here, and the area around here is almost 1. The tails are very, very thin. Okay. We need a general bound. Generally. Position called the Gaussian tails. What we want to say is something like this. What if it's not 3? What if it's 4 or 5 or t? How does this probability depend on t? So we will take the standard normal as our kind of golden standard, then we'll generalize. The standard normal satisfies the following tail. So G is greater than T. This is the tail that we would like to bound from T onward. We want to say it's very, very small. And it's actually very small. And this is what we'll prove. T, and then the standard density, the density of the normal. Which means that the tail decays exponentially fast. Actually, doubly exponentially fast, e to the minus t squared over 2. Okay, good. So these tails do decay exponentially fast. Let's prove it. All right, we'll just flex our muscles in analysis here, right? So we know how to do things like this. So probability that, how do we compute probability that G is somewhere, like in some set A? Right? It's related to the density, right? So you integrate the density on that set. You remember that? Yeah, probability. That's what density is for. You integrate it on that set, you get that. Okay, perfect. So in our case, A is the set from T onward, like this. This is our set A. So probability that G is greater than T. We integrate from T onward. That's a half open interval. The density, the Gaussian density. Okay, still remember Gaussian density? This one. Ex, that's a standard normal density. And that's expression. Okay. Good. Okay, now bad news. The bad news is that this is not integrable. It is integrable, but analytically it's not integrable. It's not. So computer, you can put it in MATLAB and it will spit you an answer for any given t. But what if it's not given? Then the MATLAB will say, oh, it's an error function. It's some special function. So, okay, so let's try to get a bound on it. So how do we do this? This is a nice trick. Change variables. X equals t plus y. Why do we do that? Because it's natural, right? We start integrating from t. So it makes sense to start x from y will start from 0. Y is just an increment. Okay, let's do this. Let's see. So we will have, okay, x squared over 2. So what's x squared over 2 in the exponent? That will be, if I square the sum, I will get t squared over 2 plus 2ty divided by 2 plus y squared over 2. Okay. Okay, let's substitute. All right, so I changed variables. So the new limits are 0 to infinity. 1 over root 2 pi. That's a good number. And now we have this sum in the exponent, so I can separate it. T squared over 2 e to the minus ty e to the minus y squared over 2 dy. Yeah. Yeah, good. I just substituted. Nothing really deep happened here. Okay. Well, of course, I can still integrate it analytically. The integral is not integrable analytically, so I have to do something. I have to give up on something, compromise. What we will compromise is this number. We'll say, okay, this is just smaller than 1. Just forget that one. Why? Why do we want to do this? Because this is the most difficult term. It is e to the minus y squared over 2. That's what's killing us. That's what makes us the integral non-integrable. The others are okay. E to the ty, you can integrate ty. It's exponential. You can integrate exponential. Okay. So that is less than 1, perfect. This number, easy, take it out. This number is actually constant too, because we integrate in y. So we can take it out. And we get 1 over root 2 pi, e to the minus t squared over 2, integral e to the minus ty dy. Ah, okay. That we can do. This thing is easy. It's just an integral of the exponential. And when you do this, it's going to be 1 over t. So do it yourself. It's one step, one line derivation. That's it. We proved it. Good. Little trick. We proved it. It looks like we gave up a lot like this, but we will see that it's actually not so much. So back to more general situation. What about two-sided tails? Now we're going to test how good we did compared to the classical three sigma rule. So we need a two-sided bound now from t here minus t, and we want two tails like this to bound them. That's easy. So by the symmetry of the density, if we take the absolute value instead, and apply this formula, you pay, instead of one tail, it will be two tails. So twice probability that g is greater than t. And so we have twice that bound, which I write this way: 1 over t root of 2 over pi minus t squared over 2. Okay. And now for general normal distribution, arbitrary mean, arbitrary variance. Well, it's a transformation, right? How do you even create a general normal around the variable? You take the standard one. Take the standard one. Now you want it has standard deviation sigma. So how do you make, sorry, standard one, standard deviation 1. How do you make standard deviation sigma? Well, you dilate it. You multiply it by sigma. Okay. Standard has mean 0, and we would like mean mu. What do? You shift by mu. So you add mu. And so probability that x minus mu is greater than t sigma, that's my tail of the error bound. That's the same as g is greater than t. If you just divide by t both sides, we divide by sigma both sides, get it? And this is less than yeah, that's that 1 over t, 2 over pi, e to the minus t squared over 2. Okay, sorry guys, it was a little too technical, but okay, now let's test. What do we know? Like every engineer knows, right? Every engineer knows that x minus mu is less than 3 sigma, the 3 sigma rule, that standard deviation, the normal distribution stays within 3 standard deviations with probability 0.997. Okay, let's test. How did we do here? Okay, first of all, we have to flip the sign, so it's 1 minus that, 1 minus x minus mu is greater than 3 sigma. And this is, we estimated this to be 1 minus 1 over 3 2 over pi e to the minus 3 squared over 2. Okay, so that's our take on this. What is it? And this is approximately, and I computed this, is approximately 9970. Ha! The exact computation known to engineers is 0.9973. So we're very, very good. This is an extremely, like, what is it, fourth leading digit. So this is extremely good approximation that we got. Okay. Now, all right, this is hard to remember. I never remember all of this. What's easy to remember? This number, we can drop it usually. Because what is this whole thing saying? It says that the tails of the normal distribution decay exponentially, just like the density exponential decay. And even more than that, there's like a little correction 1 over t, but who cares about 1 over t? Compared to exponential, it gives us very little improvement here. So we can say that this is less than 1. If t is, I guess if t is greater than 1, it's already correct. So what we proved, let's say it's a corollary. If G is the normal, this is the standard normal distribution. Well, general normal distribution is mu and sigma squared. Then it stays within t standard deviations from its mean with this probability. Let's get it bigger, with probability less than e to the minus t squared divided by 2 for every t greater than 1. So these tails are really, really small. This is mu, and this is t sigma here, and the tails are really light. They go down to 0 at a super exponential speed. And that's an example of a concentration inequality. It says that most of the time x is really like within constant number of sigmas. We can call this a Gaussian tail bound. And we'll use it a lot. What will happen next time? Good. My t is up. Your t is called who? Probably. Any questions? Yeah, we're good. Okay. Yeah, let me just tell you what happens next, because just why did I do this crazy computation with integrals? Okay, to show this concentration inequality, which is super sharp. Gaussian distribution is so nice, almost constant, almost stays within this limits. And why do we talk about Gaussian even? What's so special about normal distribution? Why are we so fixated on it? Who knows? You guys know. I'm sure you know.
Central limit theorem.
Yeah, exactly, Liz. It's central limit theorem, right? Central limit theorem says that Gaussian distribution, normal distribution, is universal. It's not a special distribution. It happens everywhere in nature. If you add independent random variables, you get normal distribution every time. And if you add even not independent random variables, you very often get normal distribution. So for many phenomena, you have normal distribution. And so it says, well, then we can carry over this phenomena that we proved, the concentration into any phenomena of nature. Okay, just by central limit theorem. Turns out this is too optimistic. And it is too optimistic because of the error in the central limit theorem. It doesn't say that the sum of independent random variables exactly has normal distribution. It says that it converges to. And when you look at the convergence, the error bound in the convergence, the difference, that does not go exponentially fast to 0. That goes only polynomially fast, like 1/√n or something like this. And that dominates. And that kind of invalidates this thing. Right? We're just saying, oh, normal distribution is so nice, it's exponential tails, everything is who cares? Because the central limit theorem has this error that completely overwhelms this exponential behavior. The exponential events make no sense because the error will overwhelm them like noise. That's what we'll discover, and then we will make a different kind of we'll jump over the central limit theorem, so to speak, and we will make a direct path to concentration inequalities with exponential power that do not require this central limit theorem step because of the high error. Okay, I should stop. So that's kind of a fun direction to go and very important. Good. Okay, people. Yes. Any questions? Yeah. All right. Don't forget you have homework due tonight in about 3 hours or so, 4 hours. And yeah, and have a good weekend, and we will see you on Monday, everybody. And I will stay here longer if anyone needs to talk to me or wants to talk to me.
Can I ask some questions about homework? Like I'm a bit stuck on one moment.
Yeah.
Like, for example, problem 5, part A, I proved that the random vectors are independent when they have 0 means. And then the first part.
Hold on. Let me open it. Okay, I can remember it off the top of my head. Yeah, just 1 second. Homework 1. And this, shall we share it maybe with people? I don't know. Let me stop sharing this first. And I will. Oh, actually, why don't I? Yeah, stop share and stop record maybe. Stop record.